Good afternoon, everyone. It's a pleasure to welcome our speaker today, Valerio Carruba. He has a PhD in astronomy from Cornell University and is currently an associate professor at the São Paulo State University, UNESP, in Brazil. He is one of the founders of the Machine Learning Applied to Small Bodies Research Group. His recent interests involve the use of deep learning for the identification of asteroids in secular resonant configurations and machine learning applied for asteroid families identification. Thank you, Valerio. Okay.
Thank you. Thank you, Angela, for the introduction. I will share my screen now. Okay, can you just please confirm to me that you are seeing the screen, that you can hear me well?
Yes.
Yeah, it's okay.
Okay, thank you. So what I would like to talk about today is a book that we are been editing for the last year and a half about the use of machine learning for small bodies in the solar system. This is a book that I edited with Dr. Evgeny Smirnov and Dr. Dagmar Oskevix from University from the Observatory of Belgrade in Serbia, the Poznan University in Poland, and we have contribution from people from 11 countries for the other chapters, like Dr. Rita Casadomingos, Safan Regibai, Anna Klimsak, Antti Pentila, Kate Volk for the part on transnet knowledge, Bryce Bolin for the part on comet, Wesley Fraser for application to moving objects, Gabriel Carità for chaotic dynamics, and Abrezon Athanasios Alves from UNESP. So this is a book that has the structure. In the first chapter, we perform a short revision of the main algorithm for machine learning, artificial intelligence. In the second chapter, we show applications for identification of asteroid family members. The third chapter is about identification of asteroids that interact with mean-motion resonances. In the fourth, we discuss the asteroid families that interact with secular resonances. Orbital dynamic around asteroids is in the chapter about Dr. Aljibai, in chapter number 5. In the sixth chapter, we talk about asteroid spectrophotometric classification. Hyperbolic object in the seventh, identification of a localization of comet activity in the solar system is chapter 8, is the chapter by Dr. Bolin and teams. Detection and characterization of moving object with machine learning is the chapter by Wesley Fraser and team. Chaotic dynamic is the one by Gabriel Carità and Abrezon Alves. And finally, we should discuss conclusion and future development in the last chapter. So what is machine learning? Machine learning is a field of engineering and computer science. Machine learning explores the study and construction of algorithms that can learn from their mistakes and make predictions about data. So this is not such an abstract concept. Machine learning is already present in our everyday life. Applications include image recognition, automatic text translation, like Google Translator, YouTube video selection algorithm, among others. So for instance, when we access YouTube and there is a choice of videos from us, this is based on a deep learning algorithm that trained upon our historic of previous selection and selected the videos that are most likely to appeal to our tastes. Computer vision is applied in medicine. We have algorithms that identify, for instance, possible cancer in scans or brains, and these are actually very effective. They are already have an accuracy of 98% or more. So what is now commonly done in most cases is to perform an analysis of the scan with machine learning and then ask the opinion of an expert to confirm if the diagnosis was actually correct or not. So machine learning approaches are divided into three categories. Supervised learning, the computer is presented with a sample of entries. The goal is to learn a general rule that maps inputs to outputs. Unsupervised learning, no label is given to the learning algorithm, leaving you alone to find the structure at its entrance. Reinforcement learning, which is usually used, for instance, for programs for like the ones used by self-driving cars. Computer program interacts with a dynamic environment. As it navigates the problem space, the program receives a return similar to the rewards, which it tries to maximize. So there have been several supervised learning algorithms that have been developed mostly in Python, but not only. There are also in R and Julia and other languages. They are available for free for the scientific community, mostly in the scikit-learn package of Pedrigosa et al. Given existing population, this method uses the known data to predict whether the new data belongs to a particular group or not. So, for instance, if you have a series of fruit, you can say that one is an apple, one is a banana, and then you provide an example of a new fruit, and the algorithm will identify if it's an apple or a banana. This seems easy, but there are problems like in-class variations. There are a lot of changes among apples. There are various types of apple: red apple, green apple, yellow apple, and so on and so forth. And bananas, there are several types of bananas. So this is a problem that sometimes is challenging because inside one single class you can have a lot of variations between the members. And this is why methods like supervised learning, deep learning can be useful to apply. So usually when you work with supervised learning, you can have standalone methods which are based on a single algorithm. One of the most commonly used is the decision tree, which essentially replicate the tree structure. Imagine that you want to decide whether you want to use a kite. A kite, you need the weather to be windy, sunny, with low humidity. So you can ask if there is wind or not, if there is the sun or is raining, if the humidity is high or low, and so on and so forth. This is automatically done by our neural network in our brains, but the structure of the decision is the same. So the number of decision nodes, or the maximum depth, is a free parameter of these models. And this is one of the characteristics of these machine learning algorithms. They depend on parameters that are free, that need to be optimized for each problem to be studied. These are not the only standalone algorithm. Of course, there are also methods like logistic regression, linear regression, so on and so forth. But it gives you an idea of what to expect. Then you have ensemble method. Ensemble methods use several autonomous algorithms to obtain a result. And we can distinguish between bootstrap aggregation or bagging, when the training data is first divided into several samples, called bootstrap sample, and the models are trained on these samples, and the results, the outcome is counted with the same weight. So this is a democratic method to count the results. Boosting, where emphasizes the clean case where the previous model made mistakes in the classification, and the autonomous models with a better performances. So when you make average of the decision is a weighted average. You give more weight to the models that perform better, and less weight to the models that had worse performances. So an example of bagging classifiers, these are the tree-based method that, for instance, is the randomized forest. So you have you divide the data in various samples. So you give it to various decision trees, and you train the decision tree over these samples, and you obtain an outcome, and the final outcome will be given by a majority vote of the decision trees. So this is for random forests, but you also have other example like trees, where you essentially sample data without substitutions, which is a variation of random forest, and so on and so forth. You have algorithms that are based on boosting. An example is AdaBoost or GBoost, or the extreme gradient boosting, which is optimization of the gradient boosted algorithm. The reinforcement algorithm track the model that provide the least accurate forecast, give them lesser weights. So the final result is achieved a weighted average result of each autonomous models. GBoost is one of the best performing model of classical machine learning, in supervised learning, but sometimes begging classifier for some problems are outperforming even XGBoost. And then we go to unsupervised learning. Here, the basic idea is to predict the status of a point based on its closest neighbors. If most of the closest neighbor belongs to a class, the point is also classified as such. A free parameter of this algorithm is the number of neighbors used for the classifications. And here you have two classes. You have yellow points and blue points. You have a star. If you are just three neighbors, based on the analysis, you would classify the star as a yellow point. But if you increase the number of neighbors, for instance, to 5, then the star would be classified as a blue point. Again, this is a hyperparameter of the model. The optimal value needs to be optimized for each data set. This is what we call classical machine learning. Then we have the algorithm based on deep learning. Deep learning is a part of broader family of machine learning methods based on artificial neural networks. Learning, again, can be supervised, semi-supervised, or unsupervised. Artificial neural network were inspired by networks or neurons in biological systems. So, deep neural network is an artificial neural network with multiple layers between the input and output layers. There are different types of neural network, but they always consist of the same components: neurons, synapses, weights, biases, and functions. This component works similar to the human brain. It can be trained like any other machine learning algorithm. And by training means that you adjust the weights and bias on for each network, for each neurons, and you obtain the best combination possible to suit your data. There are various types of neural networks that are used for solar system small bodies problems. You have feed-forward neural network when the training is done only in the forward direction. Multi-layer perceptron, in which you have inner layer, hidden layer, and outer layer or more. Recurrent neural network, where you can actually train in both directions. A long short-term memory, which is an optimization of this, which solves the problem of the vanishing gradient problems for optimization of weight and biases. Convolutional neural networks, which are mostly used for recognition of images, and they are based on multiplications of filters to the matrix which represent an image. Bidirectional feature parameter network, and efficient the zero-based network, which are neural networks that specialize in the identification of small bodies in large telescope surveys. So this was a short review of methods used in machine learning and deep learning in astronomy. And now I'm going to discuss briefly what are the topics of each chapter, starting with chapter 2, which is about identification of asteroid family members. Asteroid family are primarily identified proper element of frequency domain using the hierarchical clustering approach. This is a method where you select an asteroid, you try to see if there are neighbors within a region defined by cutoff distance. If there are neighbors, they are assigned to the family, and the process is repeated with the new asteroid until you find the new family members. One problem with this approach is that it was designed in the 90s, where there were 10,000 of asteroids, but nowadays we have more than 1.4 million asteroids with proper elements. And there is a problem which is called chaining. The AGA-CM is not able to distinguish between nearby families in region of high density. So there are methods that can obviate to these problems, and we can use a machine learning optimized by the use of genetic algorithm to do that. So this chapter reviews the use of supervised, unsupervised, and genetic algorithm for classifying new asteroid family member. And what it does is it revises a series of algorithms that of classical machine learning, like Bayesian classifier, decision tree, random forest, IAG-USP, and so on and so forth, and see what actually are the values of hyperparameter of each model that perform better, what is the model that perform better for which families. ST3 perform best in all cases with values of FP at least higher than 74%, so this was a good model for supervised learning identification of asteroid families. And by this we mean that we select a family, and we give them new asteroids that were not previously connected to any family. We ask the algorithm to identify if these objects could possibly be part of a non-asteroid family. So these algorithms are usually optimized by brute force, which means essentially you select various values of the other parameter and see what works best, or you can use genetic algorithm, which we select several machine learning algorithms, apply them to the data, and see what values of the upper parameter are best, and repeat the process until you reach desired accuracy for your model. So it has been checked if the outcome of the genetic algorithm, machine learning algorithm optimized by genetic algorithm is compatible with the brute force method, and actually it is. And this will show the difference between the two methods, which is mostly centered around 0. So genetic algorithm are secure, efficient method for optimizing the detection of new members of asteroid families. And then we go to the chapter by Dr. Evgeny Smirnov, which is the problem of identifying asteroids that interact with mean motion resonances. So usually there are 3 methods for doing that. You can select the resonant angle of a resonance and see if you oscillate around equilibrium point, and we'll discuss more this when I discuss secular resonance. You can conduct optimization of the hyperparameter by brute force, grid or a genetic algorithm like discussed here. Okay. And here we show the type of behavior for resonant angle method you have. On top, you have a circulation, so the angle is going from 0 to 360 degrees, or pi in this case. So these are non-resonant asteroids. Then you have small libration, medium libration, high amplitude libration, which is here. Then you have cases with alternate phases of libration and circulations, like the figure G and H, which are called switching orbit. Now, this can be done, the identification of this method, this behavior can be done by convolutional neural network. I will discuss this more when discussing asteroid interacting secular resonance. Or nowadays, we can actually use large language models, feed them the images of the resonances, and ask them to automatically create the code. And this has been proved to be particularly effective recently for problems with mean motion resonances. So we go now to the chapter on asteroids interacting in secular resonances. So secular resonance occurs when there is a commensurability between the precession frequencies of the longitude pericenter J and nodes S of an asteroid, the fundamental frequency of a planetary theory, Gi and Si, that go from 2 to 8 from Venus to Neptune. They are more easily identifiable in domain of proper frequencies where they appear as straight lines. And so you can see here, for example, the G-type secular resonance, which are the one associated with frequency G. They appear as straight line in this domain, proper J over N. And the same for the S-type resonances, which appear a straight line in the domain proper S over proper N. So if you plot them in standard domain like a semi-major axis inclination, they would have a complicated structure in the dimension will depend also on the values of eccentricity, which makes identifying asteroids in secular resonance a bit more difficult than asteroids that interact with mean motion resonance. So the process for identifying the asteroid status is very similar to mean motion resonance. You do an analysis of the resonant angles. The resonant angle is different, of course. It involves the longitude pericenter or longitude nodes. But here you have the two extreme cases, libration and circulations, and of course you have the intermediate cases that we already saw on the chapter with Evgeny Smith. So you can librate around an equilibrium point, which can be 0, 180 degrees, or in other cases, an intermediate value depending on the type of resonance that you are studying. So identifying this plot is nice and easy if you have a few hundreds of asteroids, but we have several thousands of asteroids, this become a very taxing task. So it's better to create these models based on computer vision. And up to this year, up to essentially February 2024, the most common method was using a convolutional neural network. So what they do, essentially, they have an image, which is a matrix. They multiply a filter over the images, which is called a convolution, and they create what is a feature map, which can be used to identify the kind of images, the kind of feature that you want to find in the images. There have been several works by our groups on this kind of application, in particular on G-type, S-type resonances. I won't discuss it further for the moment, but we'll come back on the end when we discuss future development for machine learning and artificial intelligence. And then you have neural network modeling techniques in astrodynamics. You have the use of recurrent neural network, which are ideal for handling sequence prediction problems. They're used to predict the next position of asteroid based on sequential past data, so they are very useful for time series problems, for instance. So convolutional neural network, they can also process time series data, and this is the work by Dr. Aljibai on the use on deep learning for this kind of problems. So these have been applied to real asteroids. You can actually create chaos indicators using this method based on deep learning. For instance, it can be used to predict the motion of spacecraft relative to the asteroid apophis, and to create a map of stability and predictability for these orbits. You can have the results shown here. And since they can be used for time series analysis, they can also be used, for instance, for forecasting solar flux, analyzing pattern historical solar activity data, which is important for the dynamics of artificial satellites around the Earth. Okay, so we have to chapter 6. And here, this is a chapter about the physical property of asteroids. This is a chapter by Dr. Dagmar Oskiewicz. Spectroscopic spectrophotometry as the most common types of measurement used to determine the taxonomic types of asteroids and to model their mineralogical content. Traditional spectral observation provide a reflectance over a continuous wavelength range. They allow for more detailed modeling, but can be typically obtained for a limited number of objects. Spectrophotometry, which is based on analysis of bands, provides measurement selected photometric band, is easier to obtain for a much larger number of objects. And the recent boom of large spectrophotometric service allowed the model of 100,000 asteroids at the same time. The Sloan Digital Sky Service has been one of the most used, but now we also have the data from Gaia, the data from the Dark Energy Surveys, which has been published this year. And next year, in 2025, we will have the data from the Large Synoptic Sky Telescope, or Vera Rubin, which is going to increase by order of magnitude the number of objects for which we have data. So we really need a new method, and machine learning method become crucial in analyzing large model data. And the chapter is about reviewing the recent study contribution of machine learning algorithm to the analysis, interpretation, spectrophotometric and spectroscopic data, both in terms of traditional machine learning and deep learning and method like the one used by Antti Pentila for simulated Gaia and LSST data. So this was chapter 7, and I think okay. And then we have a chapter about trans-Neptunian objects. It has been well known that they can be divided in 4 different dynamical populations: resonant, scattering, detached, and classical. And in order to identify a new object, if it's in one of these classes, you will need to do usually numerical simulation. And again, the number of objects will increase dramatically by next year when we will have the data from LSST. So this is the work by Cat Volk collaborators, where they use machine learning method to identify classes of TNOs based on already existing data, so such as supervised learning. The method that have been used mostly by this group is gradient boosting classifier, and they obtain a very good results. It matches the results of volume classifier 98% of the time, and dynamic and relevant classification almost 100% of the time. So this is, again, a method that could give preliminary results with extremely good accuracy for most of the TNOs, and leave just about less than 1% of the data to be classified by visual observer in case of doubt. So with this, will greatly improve the task of classifying newly discovered transcendental notches. Okay, then we have chapter 8. This is a chapter by Dr. Bolen and collaborators. And this is a chapter about identifying comets and cometary activity in machine learning. So Due et al. Developed TAILS. TAILS is an open source deep learning framework for identification and localization of comets in the image data of the Zwickau Transient Facility. TAILS employ a custom efficient data-based architecture is capable of finding comets in single image in near real time. And this includes the first assisted discovery of a comet, which was C2022, the first recovery of a comet, which was recovered in 2021, but first observed in 2016. So this means that instead of having to analyze several thousand images per night, we can now use deep learning and computer vision to automatically detect comets every night, and this is already producing results for the Zwickau Transient Observatory, which is a precursor of the LSST telescope. So the use of machine learning, the detection of moving object can be very helpful with respect to classical method, classical like image differentiation, like recreation, orbital linking. This is a method that can provide helpful support to these things. But the problem is that it requires human effort. Is a lower efficiency in detecting very faint objects or irregular objects. So it's not completely perfect, and there is still work to be carried out for perfecting the existing algorithm. Then we go to chapter 9, which is detecting moving objects with machine learning. This is the chapter by Dr. Wesley Fraser. Most of these methods are using convolutional neural network. Among the convolutional neural network, the residual network architecture used for shift and stack searches. There are custom CNN designed for predicting source brightnesses and uncertainties. It increased the detection accuracy, reduced the human effort in data vetting. So again, it's a preliminary work of selection. Data can speed fast the process of selecting the important result. It can handle very large database and find objects. So there have been applied to some of the existing studies, like ATLAS surveys, that has used a custom based network for classifying moving objects. So, New Horizon KBO search, application of CNN for detecting faint Kuiper-Belt objects, the Zwickau Transient Facility, deep learning model for comet detection, as discussed. And there are prospects of using machine learning in large-scale surveys like Euclid and LSST, the development of advanced network for efficient nonlinear shift and stack techniques, potential for discover a large number of minor body, enhancing our understanding of the solar system. So we are almost finished, but we have to discuss application to chaotic dynamics. Chaos is rated with sensitivity to the initial condition, which show unpredictable behavior asking for deterministic rules. This chaos of small celestial orbit with bodies within the solar system could result from close encounters, collisions, or resonance overlapping. This is the work by Gabriele Carità and collaborators. And this is a method based on chaos indicator, which is called the autocorrelation function index, which is based on the function of autocorrelation. If you have a periodic signal like a sinusoidal, it will be infinitely autocorrelated with itself. essentially, if you have a period, you can predict infinite number of periods. So if you do the count the number of coefficients that are to within an interval plus or minus 0.05, you will have a lot of indexes outside this interval. So this will be a very regular orbit. On the contrary, if you have an object which is in white noise, essentially you cannot really predict the future behavior. This will be essentially no autocorrelation with itself, apart of course the first autocorrelation index. So this will be a very low values of ASFI. So ASFI can be normalized to give you a value between 0 to 1. It can identify resonances and chaotic motion induced by close encounters. And we have been applied to method like the outcome of the non-Hilles Hamiltonians, and you can see application of regular SALI, which is a chaos indicator, and ASFI, and they were pretty good agreement. You have the results on the left and on the right. They can be used also to create a dynamical map of stability, which method of standard method like the fast-Lyapunov exponent, Magnio, the frequency analysis method, and they are in good agreement in defining the region of chaos for regions of member asteroids. And one of the advantages is that ASFI is not very responsive to chaos produced by impulsive event like close encounter with massive asteroids. So if you have a region where you have overlapping of resonances and close encounter with massive asteroids at the same time, you can actually use ASFI to discriminate between the two, because it will only be sensible to the overlapping of mean-motion resonances. So I think we can go to the final chapter. And this has been essentially what we found in this book so far. And in 2020, Fluke and Jacob used 7 categories to classify the status of advancement of application of machine learning in various branches of astronomy. They define classification, regression, clustering, forecasting, generation, reconstruction, discovery, and insight. So the first application of machine learning are the most standard, classification, regression, but then you have phases like discovery, insight, like discovery of new comets, or result of it was not available with standard method, which are more advanced for application of machine learning. So depending of the type of method used, you can distinguish between emergence of field, where people are starting to investigate application of machine learning in AI, progressing when a wider variety of approaches are used on a brush shift forecasting, discovery, and site phases, and established when essentially machine learning has become the normal methods of application in the area, and emphasis is mostly on prediction, discovery, and insight, not just application of method of machine learning. Based on analysis of the work presented in our book, machine learning has been applied to solar system small body, has been considered to be a progressing field, which is refreshing. And we can now discuss some final consideration. There were some possible trends that were noticed by the authors of the book. Kaggle machine learning competition have been shown to simulate scientific processes, like the case of the ERA mission. There are new algorithms like the vision transformer, image characterization problem, the sparse identification on linear dynamics, SINDI, method for discovering governing equation from observation data, or the use of large language model to identify the resonant behavior of asteroid in three-body resonances, that have been suggested as interesting new tools for scientific advancement. And all of them, except for the SINDI package, already have new articles that have been either published or under review. And I think I will not discuss much the very interesting result of large language method by Smirnov et al., but we have a paper by our group where we apply for the first time vision transform architecture for classifying image in S10 database of asteroids interacting with secular resonances. The VIT model is based on the transformer architecture by Wasban et al., which was originally developed for natural language processing task. So the key idea is to apply the transformer architecture related to image data without the need for CNN. It works essentially in this way. You divide the images in various pieces, like shown in the figure below, and then you find correlation between one piece and all the other pieces. And based on this map of correlation, you can actually classify the images with more accuracy with respect to standard CNN. And our results with experimenting with this model have been very promising. The VT architecture is at least 10 times faster and more accurate, reaching perfect score than classical CNN, and is even competitive with results by large language models. So this appears to be very promising result, but the paper is still under review, and we haven't yet received the first revision, so we will not talk much more about it. So to conclude, applying machine learning to astronomy is a very new field of research, but is a very great potential with many new research papers published with application of supervised and supervised deep learning in astronomy, and now large language model playing a big role in the field. So a promising future with people who are willing to make the effort to learn new methods. And already we have had this year 2 meetings with a large focus on the application of machine learning, artificial intelligence in astronomy. The 4th workshop on IA, artificial intelligence in astronomy, which have occurred in UEFA ABC in Santander in August. And in September, last week, essentially, we had an entire session of the Europlanet Science Congress, which was dedicated just to artificial intelligence and machine learning in planetary sciences, with more than 30 presentations just dedicated to these topics. So we have a research group which is dedicated to machine learning applied to small bodies. If you're interested, there are more details here. And I would like to thank you all for your attention. There is as I said, there is a new book on machine learning for small bodies in the solar system by the Elsevier Publishing House. It will be published probably in early 2025 or even earlier if everything goes smoothly. The book has been accepted. If you are interested, I can send you more details separately. Just send me an email. And I would like to thank you all for your attention. Thank you very much. I think that I can stop here and take questions now.
Thank you, Valerio. We have time for questions. Laerte.
Hi, Valerio. Thanks for your talk. I have 2 questions. The first one is about interpretability. We know that this is an issue with many machine learning methods. And since your work is interested in extracting information for asteroids, I wonder if this is an issue for you, because in science we want not only to have quantitative results, but to understand where they come from. Could you comment a bit on it?
Sure, you can do that. You can have better interpretability for standard machine learning models. If you apply a decision tree, you can actually see better what are the algorithm, what is the structure of the model. You have a fewer free parameters you can explore, etc. When you apply the deep learning models, you start having models that are essentially black boxes. You have models that have millions of free parameters. And the vision transformer, I think, is even worse. These are much more complex models. I think it will be very difficult to have a better understanding of what really goes on unless you're performing a very you're using a very simplified model. So I think it really depends on what you want, essentially. If your problem is classifying objects for simple tasks like the one we are using, asteroids interacting with circular resonance, with motion resonances. I think, well, if the code works, that's good enough for us. But if you want to have a deeper understanding, then yes, I agree that is a problem. There are already libraries that allow you to understand what are, for instance, the more important feature in a database. So they will actually select for you what is the features that are what are the best. And now I forgot the name of the library, but I can look it up afterwards if you're interested. So this is part of this, what is called
explainable AI.
Exploratory analysis. You need to understand your database in order to actually do a good work in modeling your data. Now that we are moving toward large language models, which seems to be the future, at least they will look very promising. There will be another issue that not only we will have models that are essentially very difficult to understand, but we may actually lose a bit of how to say, technical ability in people, because if you actually need what you actually need just is to write a prompt, and the large language model will actually produce the code for you. What's the point in actually learning to code very well? So this is something that sometimes worries me, especially because we do a lot of effort to learn how to code, but it's difficult to say. This field is so dynamic that it's difficult to predict what will go on, what will happen in a few months. Just to say, I think up to February, convolutional neural network were the state of the art for our kind of problems. Now they look prehistoric. So really, I wouldn't want to make prediction of what will happen in a few months. I don't dare.
Okay. May I ask another question, Angela?
Yes.
I'm curious about one of the points that you mentioned at the end of your presentation about insights. Could you comment a bit what you mean by algorithms looking for insight in databases?
Well, one of the things that has been proposed is anomaly detection. So now you can actually, is one of the algorithms that are in unsupervised machine learning. I didn't have the time to recover it in the presentation, but it's in the book. So essentially, what we do, the algorithm will look at the data. It will isolate the data that does not fit in any pattern. So it will look for objects for data that is anomalous, like the name suggests. So this has been used for detecting irregular galaxies, for instance. So what the algorithm does, if we will select some objects, some images of galaxies, and it will say this is a galaxy that does not fit any of the standard pattern. It's not elliptical, is not spiral galaxies, etc. So this could be an insight because remember that we are talking about databases that are tens of thousands or hundreds of thousands of images. So this kind of algorithm can simplify your life. Essentially, they will tell you what are the cases that are most interesting. So this could be an example of insight. Other things that can be classified as insightful. Well, in some ways, you can argue that the identification of the first comet by artificial intelligence was an insight at the time. It's no longer the case, but it was a big breakthrough because it was something that really didn't happen before. So these kind of things could be classified like insightful. But if you're interested, the paper by Fluke and Jacobs or our paper on machine learning in astrodynamics discuss more what is insightful in machine learning.
Okay, thank you, and congratulations for your book.
Thank you.
Elizabeth.
Valerio, very nice talk, very amazing results, and yeah. I have a question with regard to the chaotic system, because you showed this example of application, and then you said that there are disadvantages when you go to determine the chaotic regions when you go. Could you explore or comment more on this issue related to dynamical chaotic systems?
Sure. Essentially, what it does is it computes the coefficient of autocorrelation. So you have a time series, and you compute for instance, you have a x1, x2, x3, etc. So you can actually compute the correlation between time 1 and time 2, time 1 and time 3, etc. You will get a spectrum like the one that I've shown. I don't know if it's... Do you remember, or would you like me to show the picture?
Yeah, I remember the diagram, but if you...
Sure, I'll show the picture.
Please.
So these are the two extreme cases. If you have a sinusoidal... I forgot to... Can you see the screen correctly?
Yeah.
So if you have a sinusoidal function, you can actually predict all, if you have one period, you can predict all the rest at infinity. So the autocorrelation function will be something like this. So you have a lot of this coefficient that are above 0.5. Essentially, you will have a value of or the fraction of coefficient above 0.5, which is very close to 1 or even 1. If you have white noise, you cannot predict essentially anything. This is the definition of a noise function. So most of the autocorrelation function will be below 0.5. This will be autocorrelation function index of about 0, essentially. So you exclude, of course, the first one, because the first one is the function correlated with itself. So, of course, is 1. Of course, most of the cases are in between. You have values between 0 and 1. The closer to 1, the more irregular you are. The closer to 0, the less regular you are. So you can actually use this to predict the behavior of orbits. Here is applied to a Poincare maps for the non-ILS Hamiltonian system. But it works in astrodynamics as well. We made comparison with other standard chaos indicators. So essentially, it really depends on what you want to use it for. If you wanted to use it just to study problem of resonance overlapping, is a very good tool. It's not sensible to stochastic event. If you have something like close encounter with an object, this will not affect particularly the autocorrelation function, because it's something that happens just one time and then no more.
But variability for variability systems with variability patterns, like in the light curves, yeah, you can always identify, you know, using traditional methods, a pattern, and then in this case it might be useful, right? Sure. Because then you have a pattern, you have a physical process behind, and then you can filter this. Yeah, please go ahead.
I think it would be a very interesting application. It's this was a paper of 2021, if I remember, and the method is available on GitHub. It's a very simple code, actually. It's no more than 30 lines. If you think that it's useful, please feel free to download. If you find anything, we would like to know. You think that this application another area, we would be very interested.
Yeah, great. Thanks a lot.
More questions? No? Thank you again, Valerio.
Thank you.
Então,